Hello everyone and welcome to PC Retro Tech. In some of my recent videos you will have seen this Compaq 386S machine which I've been exploring, and in this week's video what I'm going to do is explore some of the VGA capabilities, and in particular I'm going to code up a plasma which is an effect from way back which is especially good on VGA because there's lots of colours and it's not too hard to code up. So I'm going to go through it almost like a tutorial so that if you want to grab the code yourself and see how it's done and actually compile it and run it on your machine, then you should be able to. And of course VGA would be available on pretty much anything from 386, 486 all the way through to actually fairly recent machines. So if you've got a machine that can boot to DOS, you can almost certainly run this code. And even if you can't, you can always use DOSBox. So let's get stuck into it. What is a plasma exactly? Well, I found this program called plasma.exe in a demo scene archive, and as you can see it's very slowly filling the screen with a plasma image. Now I don't know whether it's in the archive because it is a demo scene production or whether it's just an early example of drawing a plasma using techniques that would be known to the demo scene community. So what it's doing is it's using a noise function to colour the pixels on the screen, and if I had to guess I'd say it's a Perlin noise function, which is a kind of fractal cloud generator if you like. Now we're going to do things a little bit differently. We're going to use sine waves instead of noise function. The reason for that is that we can pre-compute a lookup table of values, and that'll radically speed up how fast we can draw things. The other thing we're going to do differently is we're going to use 60 Hz VGA instead of 70 Hz. You might notice that there's some flicker there on the camera, and unfortunately my poor camera can't keep up with 70 Hz VGA, and that's because it only has shutter settings for 1/60th of a second, 1/80th of a second and so on. It doesn't have 1/70th of a second. So using 60 Hz VGA should fix the flicker. Now I don't know what that band is running up the screen. It could just be some extra jazz they've added to the demo. It's really there on the screen, it's not just a camera artifact. Of course it could also be a timing issue. The main thing that's going on here is the colours are changing. Now this is a technique called palette cycling, which was used for a whole range of different effects to give the appearance of movement with very, very low CPU overhead. So instead of redrawing every pixel on the screen every frame, which would be very CPU intensive, they just changed the colours that those pixels code for. And this is just an update to the palette registers in the VGA card, which is very low overhead, and so you can get a very, very fast effect. As I said, we'll do things a little differently using sine waves, but this gives you an idea of what the other way of doing a plasma looks like. Now in order to get started with programming there's a few things that we're going to need, and the first of those is just an ordinary text editor. It doesn't matter which one you use, but I'm using the Cedar Island editor, and I like this for programming because if you hold down the control key you can jump by a word at a time instead of just a character, which makes it a lot faster getting about. You can also hold down the shift key to do copying for copying and pasting. The other thing you want to do is put the directory that the editor is into your path command. So you can see here in my AutoExecBat file I have c:\ci edit, which is where this editor actually lives. And I renamed the executable to just edit.exe, so now when I type edit anywhere on my machine it will load up the Cedar Island editor. The next thing you'll want is a C compiler, and I've gone for the Borland Turbo C++ compiler. So a C++ compiler will work just fine as a C compiler, and this is version 3.0 for DOS. You might want to make a decision about whether you want the DOS version or the Windows version. I didn't have much space on my drive, so I've just gone for the DOS version here. The other thing you'll want is an assembler, and I opted again for the Borland Turbo Assembler. This is version 5.0, and the assembler matters. For a start it has to be recent enough that it can assemble 386 assembly language instructions, but also if you change to a different brand of assembler, for example a Microsoft one or something like the recent NetWide assembler, then all of the syntax of the boilerplate code that you write around your assembly language program will change, and so if you change the assembler you're going to have to rewrite your assembly code. Now the C language is much more standardized. By and large, if you change your C compiler, you don't need to change your C code. Now these Borland programs come with installers which will copy all the files onto your hard drive. There's quite a few megabytes, especially if you want Windows versions. But they'll also tell you what you need to change in your autoexec.bat file to set your path, which I highly recommend, because this means that you can run the assembler and C compiler anywhere on your drive. And what I then do is I create a directory called projects on my drive, which is where I put all my assembly files and C files, and a make file, which is a list of instructions for how to build the program. So I just run make, and it will call the assembler, it'll call the C compiler, it'll call the linker, and it'll build the program to run. In order to create our first little program, we're going to write an assembly language file, and for that we'll just use our text editor, and we'll call it, say, test.asm. And I've already written one up here. You can just screenshot this if you want. This program doesn't do anything interesting at all. This is the start of the program, and the first thing that it does is call the DOS exit interrupt, so it'll just exit back to DOS immediately. So it's about the shortest assembly language program you could have. The .386 tells it that we could have 386 assembly language instructions in here if you want to. There's actually not any here, but we'll have that there for later on. The rest of it is just boilerplate, and you just need to type that in to make it work. Now the other thing that we need to create using our editor is a make file. And this is just a list of instructions of how to make the final executable from the test.asm that we just created. The first step is to create an object file out of that assembly file using the assembler, tasm. And the second step is to take all the object files that we've created, there's actually only one here, a test.obj, and use the linker to link them all together. Again, there's only one in this case, to create the final executable program. So once I have that, if I type make, it will just run all the instructions in that make file, and the first of those is running the assembler, tasm, to create our object file, and the second part is running tlink, the linker, to create the executable. So now if I look here, I can see that I have a test.exe, which is my executable, which I can actually just run. And now it's not going to do anything interesting. As I said, it just exits directly to DOS. But we actually have a working executable here. So that's how easy it is to create an assembly language program. The next thing I want to show you is how to interface C in assembly language. We could write everything in assembler, but it's going to be more convenient to use some C. And I've created a plasma.c for that. So if I edit that file, you can see what I put in there. It's a very straightforward program. Basically it says that there's an external function called VGA Plasma. That'll be our assembly language function. And the main program just prints a couple of lines on the screen. This will have the effect of waiting for the enter key to be pressed. And then it calls our VGA Plasma function. And finally it'll just exit to DOS. Now the VGA Plasma function is going to be in vga.asm. And this looks a lot like what we had before, but there's no start anymore because the start is actually in the C program, and so I also remove start here. And instead we've got a procedure now, and this procedure is called VGA Plasma, but notice there's an extra underscore in front of the name. So this is one of the quirks of interfacing C in assembler, that you have to put an underscore in front in the assembly function. Public just makes it available to everything else, namely our C program. And the only assembly language in here is this one instruction, ret, which will just immediately return back to the C program. So this function does absolutely nothing at all, and we'll fill in the details in here when we go to write our plasma. Now the most complicated part actually is to edit the make file. And of course this has to assemble our vga.asm into an object file, compile our plasma.c into an object file. So this of course is going to use the C compiler, and then it will link the two object files into our final executable. Now the complicated part is this line here, and basically this is probably not the best way to do it. If someone knows a better way, they can put it in the comments below. But this will work. These files are from the C standard library that contains our print functions and our getch function and so on. These are the only bits that we're writing, the vga.obj and plasma.obj, and of course it will create plasma.exe. So now when I run make, it's going to run through those instructions. The first thing it'll do is assemble our vga.asm, and then it'll compile our plasma.c, and then it will finally link everything together to make our final plasma.exe, which is our executable that we can run. So let's do that. We'll just type plasma, and it will do exactly what we said it would. It prints a couple of lines to the screen. It'll wait for the enter key. When I press the enter key, it's going to call that assembly language function. Of course, that's going to return instantly, and then the program will instantly return a DOS. So when I press the enter key, everything's going to be over instantly, and indeed it is. Okay, so now we need to start writing our plasma, and the first step in that, and the fun bit, is to get ourselves into VGA graphics mode. Well, the video mode that we're going to use is the very famous mode 13H, and this is a very convenient VGA mode to use because it allocates 1 byte per pixel. It's 320 by 200 mode with 256 colors, and that means that there's 320 bytes per line, 1 for each pixel, and then of course there are 200 lines worth in memory, one after the other. So the way to get into that mode is to select function 00 of interrupt 10. It's a BIOS interrupt that allows us to change the video mode with this function, and of course we're going to use 13H. We'll put our plasma in here, and then when we're done we want to change back into text mode. So it's exactly the same again, except now we're using mode 03H, which is an 80 by 25 text mode, and then we'll exit. So that's all there is to this program at the moment. Let's run that, and we'll see that it should change into the VGA mode and then immediately change back out of it and then exit. So it'll take just a couple of seconds to compile, and that'll give us our plasma.exe as usual, and I should be able to run that, and it'll of course happen very, very fast. So when I press enter, you see that the screen cleared. That was it changing into the VGA mode, and then it changed immediately back out into the text mode and exited to DOS. So the next thing that I want to do is put some values in the VGA memory so we can see some actual pixels on the screen. So I'm just going to put the values 0 through 255, and then I'll just put zeros for the rest of the pixels. And I'll do the same on every line, so we'll have exactly the same thing on each line, but we'll be able to see all of the VGA colors. This is the program for doing that. So here is our code for going into mode 13H. One change, we have to save the DI register and restore it again before we return, because the C compiler expects this not to be changed, and we're going to change it. So this code here sets up the address of the VGA memory. So the top left corner is at segment A000 and offset 0. One way to set 0 in assembly is just to XOR register with itself. So we put A00 into the ES register, into the segment register, and 0 into the DI register. And that pair gives the address for this top left corner. Then we have a double loop here. You can see there's an outer loop and an inner loop. And the outer loop has a loop counter of 200 because there are 200 lines on the screen. And the inner loop, well, we're actually going to have a counter of 256 because we want to set the colors from 0 to 255 going across the screen. That'll still leave 64 pixels that we'll just have to skip over, and that's what this does. It just increases the offset by 64 to skip over those pixels. Now, the only other thing we need to do here is to change the value that we're going to write into each of these memory addresses. So we'll start at 0, so we set AL to 0 using an XOR, of course, and each time the pixel loop runs, we're going to increment that value by 1. Now, the assembly language instruction for writing the byte in AL into the memory address given by the ESDI pair that we set at the beginning is the STOSB instruction. So it's a really great instruction. It does a whole load of stuff for us. It takes the byte in AL, it writes it to a particular memory address set by ESDI, and then it even increments DI after each time it runs. So it'll automatically be stepping across the memory addresses. So that's basically all there is to it. And then the final thing that I've done here is take the code for going back into text mode and put it into a separate function. And that means that I can call this after a key press in the C program. Now, I've already compiled all of this, so let's run it and see what happens. When I press enter, instantly the screen fills with color. Now, this is pretty gaudy colors. These are the standard VGA colors, but you can see that it's setting from 0 up to 255, skipping 64 pixels, and then doing the same thing on the next line, and just doing the same thing 200 times over. We'd like to change these colors though. VGA is able to deal with a lot more than 256 colors. It can just do 256 at a time. And the way that we set the colors that it uses is we set some registers inside the digital to analog converter. There are 256 registers in there which are filled with the actual color values that are in the palette. And so what we're going to do is set those registers so that we start off, say, with some reds, then go into some greens, then into some blues, and then into some whites. And that'll give us a nice gradient that we can use for our plasma effect. Well, it turns out to be pretty easy to change the color registers. There are 256 of them, and they're numbered 0 through 255. But register 0 is also used for the background and border color, so we don't want to fiddle with that. We'll leave that as black. So we really want to start at register 1, and that's what this code does. So you send the register number to port 3C8H. And then each register has 18 bits of color information in it. There's 6 bits for red, 6 bits for green, and 6 bits for blue. And so you just adjust those values to whatever color you want. So those get sent to port 3C9H. So in this little example here, which I've commented out, I send 63 to the red part, 0 to the green part, and 0 to the blue part. So this will be a pure red color. 63 is the largest 6-bit value that I can use. And then all that's required is just to do the same for all the other registers. This will set register 1, and then I do register 2 the same way, register 3, and so on. There is one trick. It turns out that once you've sent 3 color values to a register, it automatically increments to the next register. So you don't need to do that yourself. So this bit of code only needs to be there once. It's this bit that'll be repeated. So that's what these loops do. So this is a loop to give me a gradient from red through to green. All the other code here is just some arithmetic to compute what the colors should be. And I have a similar thing for green through blue, and finally one for blue to white. So let's take a look at that and see how it looks. And indeed we have a nice gradient from red through green to blue and then to white. So this is much better for our plasma, and we're pretty much ready to go with that. One slightly disappointing thing is there's still flicker on my camera, and this is still running at 70 Hz. I'm a little bit surprised by that. I would have thought the 320 by 200 VGA mode was at 60 Hz, but apparently I've got that wrong. I'm going to look into that a little bit and figure out what's going on there. But the next step for us is to write a sine table, a lookup table of sine values, so that we can use it for our plasma. So I'm going to do that now in C. It's really hard to do that sort of thing in assembly language, but it should be really easy in C. Well, I finished computing the sine table, and so I've called it sine tab, and I want it to repeat every 64 values. So it's just going to be 64 values in length. And I'm going to use integer values for this, so I've used an unsigned char, and I'll explain why in a moment. But let's have a look at the code for computing the values that go into this table. So there are 64 values, so it's a loop with a loop counter of 64. And all it's doing is it's computing the sine of an angle and then increasing the angle. Compute a sine of an angle, increase, etc. And putting the values into the table. So this additional arithmetic here is because the sine function is from -1 to 1, and working with negative values is not very convenient. So I add 1 to those values, and now I have values between 0 and 2. And I multiply that by 63.5 because that then gives me values between 0 and 127. Now, why am I doing that? Well, it's because I want to add two of these sine values together. And I'm going to take one sine value for the position across the screen and another sine value for the position down the screen and add them together. And if I add two values that can be at most 127, I get a value that can be at most 254. Now, the background color has to be avoided. Remember, the background color is in register 0, and that's black, and it doesn't fit into our gradient, so we don't want to use the value 0. So I'm going to have to add 1 to all of these values anyway, if I want to use them as color values. And so that'll mean that I'm really getting values between 1 and 255. And that's absolutely perfect because that's exactly the range of colors that we have. So that's why I've done all of that. I want these sine tab values so that I can add two of them together, one for the horizontal position, one for the vertical position, and I'll get a value from 1 to 255, which will be a color value. So that's really all there is to it. And the only other thing I need to do here is to pass that sine table to the VGA plasma function. And you can see I've just added this to the prototype here so that it says that it takes an additional argument, which is this sine table. And of course I also have to use the math library. So let's have a look at how the argument is handled on the assembly language side. This turns out to be way easier than you would imagine. So assembly language arguments are passed on the stack typically from C, and what we do is we put the stack pointer into the base pointer so that we can use the base pointer to refer to arguments. And Ball and Turbo Assembler has this magical arg thing here which allows us to specify what the arguments to the function are so we can match them up with what happens on the C side. So there's just one argument here called sine tab, and this is referred to via the base pointer. So once we set this up, Boolean does everything else automatically for us. So I can actually refer to sine tab down here just as if it was a register or a memory address. So that makes things really, really easy to handle. Now, of course, I'm using the base pointer for my arguments. So I need to preserve that because C requires the base pointer to be preserved. So I have to push it and then pop it at the end of the procedure so it goes back to its original value. But that's all there is to it. Once I've done these few lines here, I can actually use arguments passed from a C function in my assembly language function. Now the only other thing that I had to do was to modify the makefile. And this is just because I'm now using the math library. So I had to put the small version of the maths library, and I had to use emulation because I don't actually have an 8387 in my machine. But that's very straightforward stuff. I think there's probably an easier way of doing this, but I'm not going to bother just now. But let's have a look at how things work now. So I press enter. You can see that it took very little time to actually compute that sine table, and of course nothing else is going to change because I'm not actually using it for anything yet. But now we're in a position where we can use those sine values to compute our plasma. So let's get right to it. Well, as far as doing the plasma is concerned, nothing could be simpler. We already had our double loop in here for drawing all the pixels on the screen. And I've just changed this back to 320 because we now want to go all the way across the screen. And I just used these values as lookups into that table. So BX is containing the sine table, and I just pull values out of the sine table. all I have to do is make sure that the lookup that I'm doing is ANDed with 63, because I can't use any values beyond 63 because I've only got 64 values in my table. But that's all there really is to it. I have to add 1 because I want to avoid the background color, but everything else is the same. It's really just this little tiny bit of code that we had to add, and now we get a plasma. So let's have a look at how that looks when we run it. And as you can see, we get a pretty nice looking plasma. Now it's not moving or changing, and of course we'd like to do that. And the other thing is that it took a little bit of time to draw that. So if you were doing this in a demo or something like that, you'd certainly optimize this code to try and get that drawing time down as much as possible. This is still a little bit slow. So we're going to get a very slow frame rate, but that doesn't matter. At least we'll get a plasma effect working on the machine. Well, I've added the code to move the plasma about, and of course if we want to animate things we have to redraw the frame over and over. So I added a big outer loop, and it'll do 86 frames. It just so happens that my code will only work for that many frames, so that's the limit, but that runs for plenty long enough. Now of course I'm out of registers, so one trick that I can use here is to rotate the high part of a 32-bit register down into the low part, and then use it as a 16-bit register, and then rotate it back out again. And so that is as if I doubled the number of registers, which is great. So the main thing that I have to do to make the plasma animate, of course, is add some time-dependent component. And there are various formulas for this online. I just made up my own. It's basically in this piece of code here that all the work happens for the time-dependent part. And I also patch in some values that get changed. This is self-modifying code that actually alters some of the constants that are used on the fly. I won't go into all the details there. It's a little bit more technical, but if you want to have a look at the code, it is available on my GitHub account, and there's a link in the description. But this is basically all that we need to do in order to get the plasma moving. So let's have a look at what it looks like now. And as you can see, it looks a lot more interesting now. It's not so regular, and of course it's changing shape. So of course it's very slow. It's only about 4 frames a second or so, and that's because the 386 is really just too slow. We'd need to do a pixel every 3.5 cycles if we wanted to have this at the frame rate of the VGA, which is 70 Hertz, by the way. I did actually look that up. It seems I just misremembered that it was 60. In this mode it's 70, and if you wanted to do 640-480 mode, then you would have 60 Hertz. But of course that would mean more pixels and a memory layout that's not anywhere near as convenient to use. So this is probably the best that we can do on this machine. But I think it's a nice effect, and so hopefully you've enjoyed it as well. I think it's really great fun programming in VGA, and hopefully this gives you some motivation to try some stuff yourself if you haven't already. But that's all I have time for this week. Thanks very much for watching, and I hope to see you in a later video. Bye!